Hi guys, today we are diving deeper into the nitty-gritty details by implementing attention map using PyTorch image model, also known as TIM. We are extracting those precious intermediate outputs, the last layer features and attentions using the power of PyTorch hook. So it will be pretty interesting to learn what are PyTorch hooks and how to get the intermediate outputs. Other than that, I have also done the same thing with transformers implementation of Hugging Face, vision transformer implementation. There it's pretty easy as you can get the attentions from the model itself. So it's not a big deal. So let's get started with the attention maps and PyTorch
So,
image
like in
model.
the last video, we can go to PyTorch image model. So, in that, this is also called team. So, inside team folder, we can go to models. So, inside model, we can find many of the implementations to be here. So, we are interested in vision transformer. So, here, if we see, as I also glanced through it in the last video. So, here are the implementation. This has a support for multiple size of images. Like I discussed in the previous video, the model we trained is only suitable for the image size that we trained it on. But it has also support for interpolated position embeddings. So it also supports different image sizes. So here you can see in the VIT main class, the here you can see image size as the input. So here we can change the image size and dynamic image size to true, so it will support the other image sizes. Like if the model is trained on ImageNet 224 cross 224 images, it will also support 512 cross 512 images or 1024 cross 1024 images. Moreover, you can see it here, like in the Vision Transformer class, there is two functions that are called. Uh, One is in the forward function, one is forward features and forward head. In the forward features, you will get the final layer feature outputs. In the forward head, it is only for classification, the classification head that is added onto it. Here, the CLS token is taken. It self, you can see it here, or average you can do. So there are multiple options to the thing that we did earlier. So any model we are using, you can see that we get the output itself. We do If we do a forward feature, we will get a feature vector. How to get the attention in it? That is the problem. So let us start with the images. So here you can see I have added multiple images myself, and let me check if the GPU is on or not. So it is there. So I will turn it on. Let's start with images. So what will we need is input torch and input torch dot nl. Let us quickly write code for reading and writing and normalizing images. The simple stuff we'll do it here. The small basics things that mostly watching this video will be knowing already, but still I will share some basic things that I will write here. Important. And what is left? Okay, I will also add matplotlib. So I'll quickly write a config file image path. the image that you want. Let us start with a bird. This is a bird image, and also add a model path, which model config and the type of model that you want to use. So if you go below here, it doesn't matter, it will map to the same thing, but I to choose the depreciated one. So I will put an image size. We will start with, let us start with 1024 now. As in the previous implementation update, we can do 512, but let us, so there, we will write a simple function to get a normalized image, torch image, torch tensor image, and original image. It will take image path, shape, image size, and image is equal to io dot indeed. So here I will do a simple because in my images there are multiple channels, more one channel more than RGB. So I'll take the first RGB channels. So here the shape will be C, not C, H, W, C. So later I will convert it, but for now I will keep it for the original image visualization. Image dot copy for, if you have a numpy image, so you can take a copy so that the variable doesn't get replaced later. It is a simple Python thing to make copies of the variable that you want to be copied. I will normalize the image. Normalization is a basic thing that there are ImageNet mean and standard deviation. So I transform the or normalize the image to that mean and standard deviation. It's a general practice for training and inferencing your models. I will also add a batch because my one image is passed. So when I will be inputting it into input to a model, it will ask for a batch. So batch equal to 1, and I have to also. So here it is H C sorry H W C. So here I will take a normalized I will also transpose it. So how I will transpose it is, I will put image. I want C first. I want channel first. So channel is last. So I will put 2. Then I will put 0, comma 1. So H and W. So it will be done. Now it will be C H W. Now it will be BCHW after this. So my tensor is ready. I will only convert it to image into class tensor. Image. And I will upsample it, resizing it. So I have to put the image size. So size, I want to put the size variable. What will be the size? Size will be shape, comma, shape. You can get into the documentation to see how it works. But for now, I will go into it. So I have to put mode is equal to dot set. So mode will be bilinear, bilinear interpolation. So mode and here it will be image. Let us see that. Image, norm image, and image. Let us visualize the images. What will be part? Design image. Okay, is not. I generally write A. It is my practice. So usually I don't have. So here it will be which image. Here is our image, not resized with the original one. No. So it's working. Let's start with the model. Here comes the interesting part. So I want to introduce you to the concept of hook. Check out the template first. So uh, the template is you have a empty dictionary or list dictionaries, and here you have a template get outputs. You provide the name of the layer or anything. We will see it later how to use it, and you do a hook model. You put a input, you do output. You can see many implementation of it online, but I am showing the most generic one that everybody does in to get the layers. You do output, start to touch. Simple, it's done. You will return a hook. It works. So I will import Tim model equals to Tim dot create model. Now first the model name. So what was the variable name that I initialized earlier? So it was model path. So I'll put a model path. Then I will put an image. Return is equal to true. Equals to true. Then what are the other variables? Other variable is image size. Image size is equal to image size, right? So here is our model. So what I need is last layer. You can see the blocks repeating. So what I need is the last block, and this part, activation not activation. I want attention part. So here it is. 11 attention drop. Before attention drop, I have QKB, Q naught, and K naught. Okay. So I want this output of this. So what I can do is I can write a let me uh, let me first print it if I'm sure about it. So model dot blocks. So if I put model dot blocks, so I have this in the sequential. I want the last block. Last block. Yes, I got the last block. In the last block, I want attention. I got the attention. Yes, I got the attention. Now I have to go to the attention function to see if I'm doing it right. So see what I can do. Can I get the attention directly? Is it stored in a self function? So if I do a dot QKB, I will get this. Only this. If I do a, let's say, a attention drop, then I will get this. So I can get the attention directly then. It's a nice thing. The problem is, yes, I can get the direction directly, but you can see this line. So I cannot get the attention directly maybe for some reason. So can I get this self dot non? Yes, I can get that. So why not get that then? So let us do this. I will do get this Q non. So this is my target. So what I will do is I know that I want this. One thing I should do is put my model to GPU. So I have my model on GPU. Nice. I have an empty outputs dictionary. Now I wanted that, so I pressed that. So it was already model was out there. Attention. In attention, we are searching for Q norm or Q naught. Okay. So what I'll do is I will see a Q naught. I will do register. It's an inbuilt function. Register forward hook. There are two types of hook, forward and backward. You can go to the documentation to read about it. But for now, I will use a forward hook. Our function will get outputs. So I will name it. Now put the name here. It should be a string. String. So I will put the name as Q. Okay. And another name as K. So K will be changed to K. We can see it here. Let us save the feature. What will the feature? We have uh, we have saved it for the event K, but we can also get the feature here. So why not get it? So we wanted the block -1. So what will be the dictionary for that or the layer for that? So it will be -1 and I think this is it. So it should be the output of the block itself, the MLP and the block itself. So we can directly call the block. We don't need to call anything else. So we'll register it and put the name as last hidden step. At last name it as feature. So feature output of the last layer. So let us see if it works. So we'll do a forward pass. Doing the forward pass, it will automatically save the QK here features. It is the forward pass. In the forward pass, I will do image. Yeah, it should work. It's giving some error. It has no attribute. Okay, I have done some error here. So the name is output, but I'm written outputs. Now it should work. So let us see if it's working. So it's working. We will see if the outputs are listening. It's already there. So I have a Q, I have a K, I have a V. So we got the outputs. Now we can check the shapes of our outputs. So we can check the shape of Q dot shape. Nice. Okay. So it is the number of heads are 3 and the number of patches are 4096. That is plus 1, 4096 plus 7 plus 1. So it is 4097. 64 is the divided head that it has. Other than that, there are 3 heads, so 364 is equal to embedding dimension 192. And let us check the features. So it's batch size 4096 plus 1 and the embedding dimension that is 192. So we have to find the attention. So what would be the attention? It is input attention. It from here also. So we'll copy this. We have Q and K and copy this instead. Let's see. Save this and this and but it's nothing so need. We need a software attention. Softmax. But we are forgetting something that we have to scale it. Then what we'll do is we'll simply call the layer and get it from the because it already has the self.scale. See here, self.scale is here, so I think it should work. Scale, so it's 0.2, 0.1, 0.125. Scale. It's simply multiplying it, so we'll also multiply. Q is not defined. Okay. So what we will do for Q? Well, the attention. Let's say Q. So our variables are different. So it's going like Q dot K. Let us see if it works. So it works. We will check our attention shape once. So it should be yes. Now it's right. Let us visualize it. So what we'll need is to visualize this attention matrix. Let us visualize all the heads. So num heads equals to 3 here, b comma num heads comma num patches 1 plus 1 is equal to this. So what will be the size of the image that will create from the images 4096 root of 4096. So for attention maps head in range of num heads, what I will do, I will create each head one by one. So this is our attention. So its shape is 1 comma 3 comma 4096 4096. So I will take, as I did in the previous video, I will take a CLS token out. So all the head, not all the heads, I want this head. Now I want a CLS token, so I'll put a 0 here. Now all the tokens other than CLS token, but the size is 1 comma 4097. I want to remove the 4097 and make it 4096. So I have to remove the CLS token from here to make it a 4096. Yeah. So the attention now, and make it from 1 it will start. So it will become 4096. You can directly put it here, so it doesn't matter. Now I have to view it. How to make a square which has a root of 4096. So take a variable map size, make it int of np.sqrt of num patches and -1. So view 1 for batch, 1 for channel because I want to upsample it later, and what, it will become 4096 root 2 times. So we're converting a vector of 4096 into a square of root of 4096. Map size and map size. To visualize it better, I will upsample it. Dot upsample. The image size is equal to, let us get the image size, outputting the size of the image. We can correlate the image and the attention outputs then. And we don't need to change the mode because it already nearest, so nearest is fine for us. And then we'll put the attention map. So our attention map is, we have to convert it to numpy array image. So it will be 0 comma 0 comma all detach detach, to modify the CPU first, because it's already on GPU. Modify. So it's converted. Now I will visualize it. IO dot I am show attention bar. To repeat the visualizations for each one, I will put a plt dot show. So there is two value to measure the impact. So yes, we have to do it 2 times. Attention is not defined because it is attention map. Nice, we are getting the outputs. So you can see how the outputs are looking. Let us tweak it a bit. So here I have done attention. Now let us remove the scale. Let us check what happens when I am doing the experiment. Doesn't matter. Nothing appears. Let us remove the softmax. This nobody has done it. I guess nobody has done this. Oh, do you see the outputs? How good they are. What I have done is remove the scale and remove the softmax. And these are the outputs I get. Remove the softmax gives a good level of detail. It only scales it down. If I don't use a scale, then the values are larger to work with. Nice. This is enough. Like I feel we should not do the softmax here because it reduces the values to lower values. So with visualizing, I've already added the code here with the hugging face. I would add a link to it. So it is nothing the same thing. The only thing is you don't have to do this hook and other things. You can directly call the output last bin set for the last output and outputs of the attention for the attention of the all the layers. It has all the layers. So we'll pick the layers from 1 to the number of layers and you can directly visualize it without any effort to get the intermediate layers. So it works in the same way. But as I discussed here, outputs for me without the softmax are better than outputs with the softmax. So this works for me better. So this is the video. It was very easy. Only the new thing we learned is this part and how to get the intermediate outputs here. And the small thing here, we have to work with the CLS token. You have to pick the CLS token and remove a CLS so that we get the 4096 shape, all the patches, and we then plot the individual patches as they were in the image. So each patch space corresponds to the same place in the image and gives us a good output. And we can analyze our model if it's working great or not. So that's it from my side. Thank you, everyone. We'll meet in the next video.